talk about RSA and attacks on RSA. First, I'll start with going over an implementation of RSA using this Maple worksheet, and then I'll cover some attacks on RSA. I have a variety of sources, one of which is Dr. Jeremy Johnson of Drexel University. There's a paper called 20 Years of Attacks on the RSA Cryptosystem by Dan Bona. A book called The Hardware Hacking Handbook by Jasper Van Woudenberg and Colin Flynn. Sorry if I mispronounced that. Some Wikipedia articles and maybe a few other sources. So, first I just wanted to highlight a few things. One, the security of RSA algorithm depends on the difficulty of factoring large integers. There may be other ways of breaking RSA that do not involve factoring. And also the security of RSA has not been shown to be the equivalent to factoring, nor has RSA been proven secure. Factoring algorithms are known that can factor 100-digit numbers in a reasonable amount of time. And one more thing to call out is that this is an exploration of the RSA function, not to be confused with RSA cryptosystem. The difference here is that the RSA cryptosystem is semantically secure. If given a public key, it should be intractable to recover any information about the plaintext message. The RSA cryptosystem achieves this by inserting randomness. However, for this presentation, I wanted to focus on attacking RSA and the math behind it, so I did not insert that randomness. However, we'll see that the susceptibility of RSA to these attacks are mostly by virtue of improper RSA implementation. However, they're worthwhile studying because RSA is non-trivial to implement correctly. So as I mentioned, we'll start with the RSA implementation. The components of RSA, so P, a prime, Q, a prime, and these should be large as I discussed already. N is the product of those two primes. E, where the greatest common denominator of E and phi of n equals 1. That's called Euler's totient function. There's a link to it here if you'd like to read more about it. D, where D times E is congruent to 1 mod phi of n, and a message M, which we're encrypting and decrypting. The keys are comprised of the exponent E and N for your public key, and the secret key is the exponent D and N. In order to decrypt or decrypt messages, we have two functions. So the encryption function is raising the message to the E exponent mod N, and decryption is message raised to D mod N. Signature, that's another property of this. So you can take your message and run your decryption algorithm on it, and then others who have your public key would be able to run your encryption function on it, and if the result of that matched the plain text message, then the signature is valid. So without going into too much detail, a lot of this was just taken from Dr. Jeremy Johnson's Maple worksheets. But possibility string is essentially our alphabet. Here we can just see that the letter A is this char code function will return 0 for that since it's the first here. Convert block is basically about being able to translate that string into a number. So here I'm just showing that we took the string hello world and we have converted it into some numbers. So capital H is 48, lowercase e is 4, and so on. Here I'm just again kind of showing how this all becomes one large number. Block string, so this is just taking that number and converting it back into to a string. So this here is worth mentioning that this is not encryption, this is just encoding. So we're taking a number and encoding it as a string, or a string is encoding it as a number. So I'm showing it because when we encrypt stuff at work, we're kind of used to dealing with strings. So I'll get into that a little bit more in a moment. Yeah, that's kind of what I was saying here. We're going to be sort of combining encoding and decoding along with encryption and decryption, but I don't want those two to be confused. The other important thing here is that for a given n, we may need to break our message up into lengths of n. So that's what this function does here. It just takes our encoded message, which is this big number, and turns it into a list of numbers. And then unblock will turn those lists of numbers back into a single number, which you can see here is equivalent to our encoded as a number message. So here's a full example. We've got a prime P, a prime Q, N, which is the product of those. So you can see the result of that here. Maple has this number theory package, and inside of it is a phi function. And here I was just showing, well, one, what phi is in this case, and also I was showing that you can calculate phi of n this way. E, we choose a random E that matches this condition, okay? So integer greatest common denominator of E and phi of n equals 1, and we'll just keep guessing randomly until we choose an appropriate E. D, we'll take the inverse of E mod phi of n, and now we have our decryption exponent. So in this example, we've got the string hello world. We'll encode it as a number. We'll block it into a list of numbers. Then we loop through each of these numbers and we encrypt. So just scrolling back up here a moment. I mentioned that the encryption function is raising the message to E mod n. So that's what we're doing down here. Then we're going to take those encrypted blocks and just make it one big number. Then we can convert it to a string. So hello world, when it's encrypted, now looks like this. And now that we have encrypted our message, we can decrypt it. So we want to go back to a number. So from the string back to a number. Then we're going to block that number. We're going to iterate over each block and decrypt it. Then we'll take those list of decrypted integers, turn it into one integer, and we'll convert that back into our string, and we end up with the plain text message. So that's a round trip of how this all works. So now that we've reviewed that, we can go over a few different attacks that we can do on RSA. I've listed a number of them here. We can do a brute force, so Maple, which this presentation is written in, has an integer factoring function. So if P and Q are not sufficiently large, as I mentioned before, then factoring them is not such a challenge. And RSA relies on the difficulty of factoring large integers. So in this example, we have n, we have this E, and assume we have this ciphertext. And let's just say that, okay, so this is a ciphertext as an integer, and when we get it as a string, it looks like this. So this might be the string we're looking at, the encrypted message. In order to decrypt this message, an attacker would have to factor n. And that means arriving at P and Q, which n is the product of those two numbers. So since E is part of the public key, that's known, and n is also known, that's the other part of the public key. So what we need to do is calculate phi of n so that we can then derive D. And here we're using Maple's I-factor function, and I have it printing out the results down here. So we've got P and Q. It was able to factor in for us. Once we had P and Q, we could calculate phi of n, and with phi of n, since E was given, we could then calculate B. And here I'm just doing a few backflips to to deal with the encoding and blocking and unblocking and so forth. But the actual decoding is happening here. This is the decryption function that I basically described at the beginning. And you can see here we arrive at the plain text message. So we have effectively broken RSA there. Okay, so that is why you should make sure you use sufficiently large primes for generating your n. Now, another attack is the common modulus. So according to Bona and 20 years of attacks on the RSA cryptosystem, it's convenient yet unwise to avoid generating different modulus n equals p times q for each user. So obviously it's tempting because it can take time to generate these large primes and create an n. And what's more, the keys look different because, well, they are. I mean, you have a different, you could use the same n and a different e and a different d, and the key pairs would look different. But this is not safe. And let's see here. What else did I say? Okay. So, yeah, it's not safe. Let's explore why. So, in the previous example, we had E, which I'm storing as previous E now. So we're going to calculate a new E, and we're just making sure that it's not equivalent to the previous E and going through our conditions in order to get a valid E. And once that's been obtained, well, as you can see here, the same n has been used. So because the same n has been used, basically we're able to derive, we can use our new E, and we don't need to do anything more about P and Q. We can just decrypt the message now, and we arrive at the same plain text message. So that is why it's unsafe. The keys are different, but the n is the same, and you can see here why in this scenario, I mean, I didn't walk through the whole thing about factoring P and Q out, but you can see how even though the keys are different, if one were compromised, they all would be. Okay, so now blinding, I did mention signing documents with RSA, that's a property. Blinding is basically a forgery technique for signatures. So by comparing, okay, yeah, so we'll walk through this example, but the kind of idea here is if somebody asks you to sign a document and you refused, and then the attacker did what's called create a blind and asked you to sign this blinded message and you obliged, then they could forge your signature on the unblinded message. So let's see here. So we've got an N, we've got an E, so our public key is here, and the private key N is here, and D is there. Our message is 1, 2, 3, 4. And this is just walking through an example of signing a document. So we run our decryption function on the plain text message, and we get the signature. When we run the encryption function on it, we can see that the result of that equals the plain text message, so the signature is valid. Now, again, this attack is a little contrived because I don't know why somebody would ask you to sign a message and you refuse, and then they ask you to sign this other message and you agree, but that's how the attack works. So in this case, the attacker could ask you to maybe, let's say the attacker gave you this message of 1, 2, 3, 4, you refuse to sign it. Then the attacker could blind the message and ask you to sign the blinded message, which you would oblige, and then they could use that to forge your signature. And they do that. They create that blind by choosing a random R, and then they have this, they use R to calculate M prime. And when you sign M prime, now the attacker could compute your signature of M. So here we're just generating a random R, which I printed out. In this case it was 2. And there's a formula to basically create this blinded message, so we create it. And in this example, they would give it to you, and you would say, okay, sure. So you sign it, and now the signed blind message looks like this. Okay, so the plain text message was like that, the blinded message was like this, the signed blinded message was like that. And then here, they're able to take the modular inverse to R modulo n and forge your signature on the original message that you had refused. So here you can see that M is 1, 2, 3, 4, and when we run our encryption function on the forged document, it does in fact equal 1, 2, 3, 4, the document that you did not want to sign. So they successfully forged your signature. And here it's just saying, yes, the forged equals the signed. So it's just showing again that the forgery appears to be valid, or appears to be authentic, and the forgery worked. Okay, small private exponent in RSA cryptosystem. Bob might tend to use a small value of D rather than a large random number to improve the RSA decryption performance. Wiener's attack shows that choosing a small value for D will result in an insecure system, which an attacker can recover all secret information, i.e. break the RSA system. I have a link to a Wikipedia article here. So we'll walk through this attack here. So basically this attack, I took it from Wikipedia. I just wrote it out in, they were just using mathematical terms. I actually wrote it in Maple here. But long story short, we have N and E. And we use continued fractions to, and here in Maple we can wind up with a list of convergence. So we iterate through them, and we try to find, so like we try to, here I said we don't want it if it equals 0 because that first convergent would obviously not produce a factorization event. The second one does, which is 1/5. And so there's basically a formula that we can use. And we calculate rho of n, and we solve this quadratic equation. And the result of that quadratic equation will give us P and Q. And I have it all printing out down here. So P and Q are 379 and 239 respectively. And we calculate phi of n. And once we have phi of n, then we can calculate the D, the decryption exponent. So that's why it's a bad idea to use a small private exponent. Small public exponent, also bad. To reduce encryption or signature verification time, it's customary to use a small public exponent E. The smallest possible value for E is 3. But to defeat certain attacks, the value E equals 2 to the 16th plus 1, or 65,537 is recommended. This talks about Coppersmith's theorem, so that forms the basis of a lot of different attacks. However, we're just going to focus here on one of them, which is Hastad's broadcast attack. So in this attack, imagine a scenario where one sender sends the same message in an encrypted form to a number of people, each using the same small public exponent e, say 3, and different moduli, so different n but same e. The article goes on to assume that an attacker intercepts the broadcast messages, so an attacker received all 3 of the ciphertext messages, and the attacker is able to use Chinese remainder theorem to calculate c equals m cubed, and then they need only take the cube root of c to arrive at the plain text message m. I left this little note because I found it in Wikipedia and in Bona's article, but wanted to highlight it here. For larger values of e, more ciphertexts are needed. Particularly e ciphertexts are sufficient, according to Wikipedia. Bona states that this attack relies on all public exponents being equal to e, and that the attack is feasible only when a small e is used. So that's important. Oh yeah, and I just went with like the simplest version to show this. Halstead also showed that you could make this attack like seemingly harder by applying different paths to the message so that recipients receive slightly different messages. But Halstead showed that that does not protect against this attack. So we've got the same message, different ends as described, and the same E, which is small. So we have different ciphertexts of the same message. We use Chinese remainder theorem to derive x, and we just take the cubed root, and here we can see that the recovered message is indeed 1, 2, 3, 4, and here I was just printing out that it's equivalent. Okay, timing attacks. Measuring the time it takes to run RSA instructions. Private key can be leaked. So, all right. Bona provides sample RSA implementation that he refers to as repeated squaring. The Hardware Hacker's Handbook refers to this as modular exponentiation algorithm, but they're describing the same thing. So this is from Bona's work. He says set z equal to m and c equal to 1 for I equals 0 to n, do these steps, and so on and so forth. This book actually provides the code. So here they say secret data. What they really mean is a secret key. So in our case it would be like a D. M is the familiar message, and so when we compare this to what was described in Bona's paper, set z equal to m. So they're using s instead of z, and c equal to 1, so they're using p instead of c. But you can see that they're effectively describing the same thing. And what I was trying to highlight here is that for the secret key, this is doing a bitwise and if the least significant bit is a 1, then this other operation will take place, and if it is not, then it will not. And then they do this bit shift down here. So if you have like an oscilloscope or some other way of measuring the time that this algorithm takes to run, since this always runs once you're past the first, like once I is greater than 0, it will basically allow you to read D out of the traces. And of note, they're just going from 0 to 10, so in practice this would be like your secret key isn't going to be 10 bits long. I mean, it's going to be thousands. But for demonstration purposes, this is fine. And this is from Hardware Hacker's Handbook. Somebody there had provided this trace, which I then tried to highlight it with these green and blue dashes. But basically, you have these the x-axis is time and y is power, so you can just see how long each of these take, and presumably when you have 2 operations it takes longer than 1, and because this only happens when the least significant bit is 1, we know if it doesn't happen it's a 0. So when you have like short long, then you know what ended up happening was this, then this, you know, the square, then the multiply. So you can take two of these together and say, okay, if it's green, blue, that's a 1, because you know that secret data's least significant bit was 1, and it loops through each, and you're able to read out what the secret key is. Okay, so that is timing attacks. All right, so the last thing we'll go over is power cryptanalysis. So you can measure power consumption of running RSA instructions and read the private keys out. So this is my oscilloscope. And basically, the attack I'm about to describe, it relies on the observation that each microcontroller instruction has its own characteristic appearance in power consumption traces. So a multiplication operation can be distinguished from a load instruction. And microcontrollers use different circuitry to handle multiplication instructions from the circuitry they use when performing load instructions. That's why it works. So the result is this unique power consumption signature. And one reason why this is interesting, after having just looked at like the timing attack, is that in RSA implementation, I mean, you could imagine where they might want to put like a random delay between each loop, and that would make the timing attack either not possible anymore or certainly much harder, where this power consumption would be more or less impervious to that. And let's see, what else more to say about that. This example I'm going to show, I mean, I was using a password, like kind of checking a password bit by bit rather than the timing where we're checking like a secret key, but obviously it's the same idea still applies. So let's see. So in this example I'm about to show, I have this scope. I have an Arduino Uno, which has a ATmega 328 microcontroller, and I had to use a 100 ohm shunt resistor so that I could have my scope read the power out of there, the waveforms. And also, this particular example that I'm walking through, the code from it is from the Hardware Hacker's Handbook, which does have this random delay inserted, so it does remove the ability to do the timing attack. You have to use, like, examine the waveforms. So this here is my Arduino Uno. This long rectangle there, that's the microcontroller, the ATmega 328. It's nice because this comes in a few different flavors. The ATmega 328, it can also, this is called a DIP, a dual inline package, but sometimes you'll see them as like little square where it's got like little legs that are soldered right to the board, and I didn't want to have to solder anything. And this dual inline package, you can take a screwdriver, well, they have little tools you can use, but I usually just use a screwdriver, and you can pry it off of there and pop it off, and then put it onto a breadboard and kind of transplant it that way. Okay, yeah, I think that's all I really have to say about that. So here it is again. I've pried it off. And okay, so here, this is the pinout for that ATmega 328. So at the top here we've got this purple reset, so we're going to wire that up. The two pins below that are RX and TX, so that's for like UART, you know, serial communication. So what I did was I have like a USB UART that I could hook into that. Then let's see, what else do you have? You've got the voltage and ground, so obviously we're going to have to power this thing. You've got digital pin 4. I'm not going to really, I'll describe it briefly, but it's not really super related. I was using it as a trigger. Those two green crystals, those are magic crystals. As most people know on little hardware devices, those are used for a clock. And I think that's pretty much it. Reset, digital pin, voltage, ground, crystals, you know. So here it is wired up. I transplanted the microcontroller onto my breadboard there. On the bottom left, there's a blue wire, that's ground, and the red wire next to it is hot. Yellow wire is reset. 2 red wires in the middle are the crystals. 2 green wires are for serial communication, so that I can plug the Arduino in and send my keyboard commands there. You've got condensers that are just there to try to smooth out some noise, and the little wires that are coming from the rails on each side bring the power in, and of course the shunt resistor. And this is the same thing, but now I've got my oscilloscope probes hooked up. On the right, you can see the probes have 2 different white wires, and one is going to ground and the other one going to a pin near the yellow wire. And going back to the pinout, the yellow wire is reset. 2 below it are serial, and the one below that is a digital 2. The reason that's there, like I said, is just as a trigger. If you're trying to capture these waveforms, you're reading a lot of data very quickly, so it just helps me to kind of zoom into the area of interest. And the other probe on the left, the lower wire is next to the resistor, which is a shunt resistor, and the other one similarly is connected to ground. So this is just so I could take these readings. And here, so the pink line is the digital pin I was using for a trigger to start recording, and the yellow waveform is the actual power consumption of my microcontroller. So you can see when I entered the correct password at the top versus the incorrect password at the, the incorrect password at the top and the correct password at the bottom, you can see how the waveform is different for the letter A. And here, I was just doing I love A. So I'll just kind of toggle so you can see the difference in waveforms. And that's basically how you'd be able to do a power analysis task. You'd look for these waveforms and you'd see which one is actually like a signature of the correct waveform, and you'd be able to read out the secret key in sort of a similar way that they're able to do it here with this timing attack. And finally, for the conclusion, what I found after exploring this is that the attacks on RSA is essentially a misnomer. It's really more attacks on incorrect RSA implementations. And that's it. Thank you.